Hi, welcome to Mendelev's restaurant. I'm Tyler. I'll be your waiter this evening.
Hi.
We have two specials today, if nothing on the menu interests you. First, we have our molecular meal, C6H12O6, or for our friends on a diet, we also have our empirical diet, CH2O. So you have two choices for your special, if you want to go ahead and pick one of those.
I think I better take the molecular meal because I'm not really sure what's in the empirical diet. What's the molecular formula for the empirical diet?
That's a good question. I can go ask our chefs.
Welcome to the post-class video. And what we're going to be talking about today are really two things. We covered percent composition in class, which it seemed like everybody pretty much got, and so we're not going to talk any more about it here. And then molecular and empirical formulas, which we spent most of the time on, and then balancing equations. And I'm going to spend a little bit more time on that because we didn't really get to it in detail today in class.
So Dr. Godes, I noticed you didn't go with the empirical diet when you ate at Mendelev's.
Right, because the empirical formula is the simplest whole number ratio, and it doesn't really tell you what the compound is. It tells you the ratio of the elements, 1 carbon, 2 hydrogens, 1 oxygen, but it turns out there are a few different compounds that have that ratio. And I've drawn up on the board here 3 of those. The first one, formaldehyde, CH2O. And that's actually both the empirical and molecular formula. It has a structure like this. It turns out this is highly carcinogenic, and so I certainly wouldn't want to eat that. The second compound, acetic acid, C2H4O2, if you divide these all by 2, you get CH2O. Same empirical formula, but different molecular formula. And this is the structure of acetic acid. And acetic acid is the main component of vinegar, and so while I like it on my salads, I don't think I'm going to order straight acetic acid. The third example is glucose, C6H12O6. And if we divide those by 6, we get CH2O, so the same ratio. And this is the formula of glucose, and of course, glucose is one of the forms of sugar. And so I might want to have some glucose, you know, if I'm not watching my weight too much, because it's pretty high calorie food.
All right.
Right, so that illustrates the difference between molecular and empirical formula. Empirical formula, the simplest whole number ratio, empirical diet, and molecular formula, which tells you actually what specifically is in the molecule. So you all understand that formula is just a ratio of elements, a ratio of atoms, or a ratio of moles. And so I thought I'd go through an example of calculating an empirical formula, just so that you have something for your record, or if you're challenged with this, you have another example. And so the problem I'm going to do is a compound is 47.6% zirconium, 15.32% silicon, and the rest is oxygen. What is the empirical formula? So I noticed that it doesn't tell us how much oxygen there is. So how are we going to figure out how much oxygen there is?
I'm going to go with subtraction.
Subtraction, because everything has to add up to 100%. And so to figure out oxygen, I add these two together and subtract it from 100. The remainder should be the oxygen. So 100% minus the 47.6% zirconium minus 15.32% silicon equals 34.92% oxygen. So the trick we learned in class is if we're given percents, I can assume a 100-gram sample. And if I have a 100-gram sample, well, what's 34.92% of 100 grams?
34.92 grams.
34.92 grams. And so I can treat the percents as if they're grams. Now, the ratio in a formula is related to the moles. So if I have grams, what's the next step?
Well, you'd want to know what that is in moles, because the ratio is in moles, not...
So to summarize, we're given percents, we assume 100 grams, we go to grams, convert the number, and then we have to calculate moles. How do we calculate moles? Grams divided by the atomic mass, or the molar mass of the atom, gives us moles. And so we took the grams, and we used the molar mass of zirconium, which is 91.22 grams per mole, And I decided that since I have grams on the top here and I want to end up with moles, I put the 91.22 grams underneath the moles. That way the grams are going to cancel out and I'll get moles of zirconium. Right? And we did that, the same thing, for the silicon and for the oxygen to get our moles.
Okay, so now that we have our moles here on the right side, we want to find out what their ratios are to each other so that we can find out the empirical formula.
And so what I do is I write out these moles as coefficients in a formula. And obviously that's not a whole number ratio. So the trick, again, is to divide by the smallest number of moles. And so I divided by the smallest number of moles, and now we can simplify the fractions. And what do we get, Tyler?
We get zirconium would be 1, silicon would be 1, and oxygen would be 4.
Great. And that's our empirical formula.
Right, but we would take out these 1s because when they're 1, you don't really need to write them, right?
Okay,
So
correct.
we have 1 zirconium, 1 silicon to 4 oxygens.
Yep, and that's the formula for zircon, the mineral zircon, which is used as a substitute for diamonds and really cheap jewelry.
Okay, so this is our third goal today, right? Balancing equations.
Balancing equations, exactly. And so what we'd like to do is just do an example. And so here we have an example of what looks like a fairly complicated reaction. Turns out this is a mineral, the formula for a mineral, and minerals out in the environment are exposed to water and carbon dioxide in the atmosphere. And so they undergo chemistry and they decompose sometimes. So let's balance this equation. How do we start?
Well, I would start by counting the number of atoms of one type of element on one side and comparing it to the other.
Okay, so let's start with the iron. And what you don't want to start with is an element that is in every single compound. Those are going to kind of come out in the end. You want to look for elements that are in only one place on each side of the balanced equation.
Okay.
And so the iron only appears once here and only once there. So there are 3 irons here.
Okay.
How do we make 3 irons there?
Well, we only have 1 iron, so we definitely want to multiply that by 3.
Right, and remember we put it out in front, you don't put it down here because that changes the identity of the compound. Well, when we put a 3 there, it multiplied all this by 3, right? And so that means I now have 3 carbons and 9 oxygens, but I have oxygen over there, and so I don't know how oxygen is going to play out. Carbon only appears once over here, it only appears once here, so now I can balance the carbon.
Yeah, let's do
So I
carbon.
go back over here.
We have 3 carbons here, and you have only 1 carbon over there,
Yes.
Dr. Godez.
So I better put a 3 there as well.
Alright, now we're equal.
Now we're equal. Okay, so I balanced the iron and the carbon. This also changed the oxygen, so I'm glad I didn't think about oxygen. So again, oxygen's everywhere. Hydrogen is in a few different places as well. So I'm going to next focus on the silicon.
Okay.
Si2.
Well, I only have 1 over here, so I'm going to have to multiply this formula by 2 to give me the same amount of silicons that you have over there.
Okay. So we balanced the iron, the carbon, the silicon, and it looks like everything else appears in multiple places. So let's look at the oxygen now.
Okay.
So how many oxygen do we have on the reactant side? I have 5. 4 times 1 is 4, so that's 9 total there. 3 times 2 is 6, so I'm going to keep track of this. I'm losing track in my head. 9 oxygens from that, 6 oxygens from that, 1 there.
Okay. And I have 9 oxygens here.
How'd you get 9?
I multiplied 3 oxygens times 3.
Yeah, because this 3 means 3 times that whole thing.
Right. And then here I would have 4 times 2, so I have 8 oxygens here. And so that gives me a total of 17 oxygens, and you have not quite enough, Dr. Godez.
I don't have enough, I only have 16 oxygens. Well, I can't change this because that'll mess up the iron. I can't change this because that'll mess up the carbon, so I'm going to change this one. I need 1 more, so I'm going to double that.
Okay.
Okay.
And now we're equal on the oxygens because you just added 1 more here.
Yep.
That gives you 17. Alright.
So we'll check the last element, and the last element better work out because everything else is balanced, right? And it's kind of a double check. So you do your side, I'll do
count my
mine.
side, okay.
And I'm going to put them up on top.
Okay, good idea. I only had them in one place. I
Oh.
confused myself.
So I have 4 H's, total of 8.
And I only have 2 times 4, so I have 8 hydrogens.
So it's balanced. Right? And so the process, you start with things that appear in as few places as possible. If there's an element by itself, leave that to the end. It's an iterative process. I balance one thing, I see how that affects something else, I go back and forth. The last step is to check. Make sure that all the charges are balanced, 0 charges on both sides. This one's easy. Make sure that the number of atoms on each side is balanced, of each type. Easy peasy, right? It just takes a little bit of practice.
Yes.
Thanks for watching.